My name's Bob Felderman, and I work in the platform networking group here. And I have the pleasure today to introduce this morning's speaker, Van Jacobson. For a lot of you, I presume Van needs no introduction, but I can't resist going ahead and saying a few things. Van's been working for a lot of years on some of the most interesting and most difficult problems in networking. And really beginning with his seminal paper, which a lot of you probably read, called Congestion Avoidance and Control, which was a SIGCOMM paper in '88. He's authored dozens of papers in RFCs and been working in this area for a long time. And in addition to sort of having big ideas and solving a lot of theoretical problems, Van is one of those rare people who can also really get down into the code and really solve the problem at the bits and bytes level. He's contributed to a lot of tools that you probably use every day if you're in the networking area, things like traceroute, pathchart, TCP dump, and many other things. Many of you are no doubt familiar with the VJ header compression, which was originally used on low-speed links but still exists in lots of networking technology today. And back when Van was at LBL, Lawrence Berkeley Laboratory, he was one of the leaders in creating what was called the M-bone, or the multicast backbone, and developing a lot of tools, things like some of you may remember VIC and VAT and WB. They were audio, video, and shared whiteboard over the internet long before people believed this kind of stuff was even possible. In the past few years, Van's work has been recognized with things like the 2001 SIGCOMM Award, the 2002 IEEE Kobayashi Award, and in 2004 he was elected to the National Academy of Engineering. And generally they were citing major contributions to the understanding of network congestion, the development of congestion control mechanisms, enabling the successful scaling of the internet, and he's really widely been credited with preventing the congestion collapse of the internet in the late 80s and early 90s. So I think Google probably owes Van a vote of thanks, because we might not even exist today if the internet hadn't been able to survive that scaling. And on a quick personal note, I just wanted to point out that I had the good fortune to work closely with Van over the last 4 or so years prior to I joined Google. And frankly, I've never seen anyone who could learn so much about what's going on in a network topology or between two hosts simply using a TCP dump file, an awk script, and the simplest little graphing program I've ever seen. And it just amazed me. I used to take our software team over. It was kind of the pilgrimage over to Van's office to kind of have him read the tea leaves for us, and we could look at the graph and he would say, see, it's obvious. This is a Linux box talking to a Solaris box, and it's dropping packets here, and it's doing this and retransmitting. And you know, it was, wow, if we could only figure out how to do that, it'd be great. One note, this is being recorded. It will go up on Google Video, so if you have questions at the end, if they are the least bit confidential or are talking about internal Google kinds of things, let's hold those questions until the videotaping is done and we can talk afterwards over lunch. And now, without any further ado, Van Jacobson.
Bob, for someone who's not going to give an introduction, that's way too much introduction. Thanks for coming. This is a really pompous title for what's going to be a really pompous talk. It's a hard talk to give. The motivation behind it is, it seems to me, for at least the last decade, network research in the US has been really stuck in a dead end. It should be just a wonderful time for networking, because we've got everything connected to everything else. We've got ubiquitous wireless, we've got phones that are starting to show up on the internet, we've got this huge wealth of information that was created by the web. We have things like Google that are indexing to make it easy to find stuff. But kind of every day, everything we're doing with the network gets harder. Wireless just barely works. You know, if you're on a campus, you can make it work. If you're wandering around, it doesn't. Every one of us is spread over multiple devices. You know, I've got 2 laptops, 2 desktops, home computer, phone. None of them are ever in sync. None of them have the information that I need on them when I need it. And the tools that are coming out to help solve those problems are really ad hoc. They're kind of point tools. And it seems like there's got to be an architectural problem because the problems seem to be so ubiquitous. I think there was a similar time in the 60s and 70s where there was a view of what networking was that was basically networking was telephony, because communications in the 60s and 70s, for almost all of the 20th century, communications was telephony. And people were trying to make data work over telephony, and they just failed miserably because data is not telephony, and telephony is not the only way of communications. And I think we're stuck in a similar thing. It's not that the solution we've got, that the internet is a bad solution, it's just the problem has changed. And so we're in a world, you know, it's kind of like the Copernican revolution. We put the Earth at the center of the universe, and we're trying to figure out planetary motion. And you can do it, but it's just incredibly complicated because your point of view is wrong. The Earth isn't at the center of the universe. And if you make a little bit of change and put at least the sun at the center of the solar system, then suddenly everything gets a lot simpler. Both systems explain stuff, but one is just a lot simpler and a lot easier to work in. And I think we're kind of on the fringes of a Copernican revolution in communication, and I'm going to try to motivate that. I'm an old fart. They say when you get too old to think, you reminisce. So I'm going to try and motivate it by reminiscing about some history about that 60s and 70s change, try and relate it to what I think is happening now. So starting turn of the century with the phone system, I had spent 20 years talking to telco people in the process of trying to work out the internet protocol, and it's completely different mindset. And it took a long time for me to figure out that the phone system isn't about making calls. That's what we use it for, but that has nothing to do with the system. The system is about wires. And if you think of its context when it was created back in 1870, there were no wires. And the goal of the system, what Bell had to do to make a telephone system, was get wires everywhere. And it's enormously costly to do that. You need land, you need right-of-way, you got to pull the pair, and you're not making any money while you're doing that. It's all sunk costs. So what he had to design was a business model in the system that would get ubiquitous wires. And as soon as he got that, as soon as there were a lot of wires to connect to phones, then he could start making revenue by people making calls. With that focus, the thing that people are doing with your system and what the system does inside are completely different. The calls that you make are 100% side effect. And what the system is doing is trying to build a path through its wire matrix. And this causes a little bit of cognitive dissonance when you're talking to telco people, at least it did for me. Because I think of the endpoints. You know, I pick up my phone and I'm calling my mom in Phoenix, and I think of her phone number as it's the name of her phone, and I want to talk to the phone named mom's phone. For telco, it's not that at all. The phone number is a program that you're sticking into the system to build a path through the wires. And that's how they view it internally. See if I can make that more concrete. So when I was growing up, this was how phones work. You pick up the line, you say, I'd like to talk to 1234. And some operator goes, 1234, so that's column 12, row 34. They walk over on their switchboard and they plug in a jack, and they're connecting your wire to a particular outgoing line. So the phone number is a 2D coordinate on this switch matrix. There was some human factors work that said one person can reach 100,000 wires. They can conveniently work in a 10 by 100 grid, and so that's why we got 4-digit numbers. This is another way of finding a path through the system. This is from the first telephone switch, Stroger switch. MIT used these up until 1990, I think. They were invented in 1890. So you've got one wire coming in at the bottom. You've got a 10 by 10 switch matrix. Every time you dial a pulse, the switch clicks over 1. So you dial a 1, it'll click over 1. If there's a long pause, it locks. And then when it gets the next pulse, it'll drop down 1 for each. So you're picking a 2D coordinate, 2 digits in, picking one of 100 output wires, and you cascade 2 of these. You can do the 4-digit 10,000 lines that you had in an end office. But your number, again, it's a program for this switch. Right? It has nothing whatsoever to do with the phone that you're calling. It has to do with connecting wires going through the system. So this works, right? Completely revolutionized communication. It did it as a side effect, but it was the only way it could have been done given the economic constraints. Right? You had to get the wires in place. You had to make this base communication system. And then you had to figure out how to efficiently use those wires. Perfect. It's got some structural problems if you try to take it out of the context of people making calls to other people. One issue that sort of Judge Green solved for us in the 70s was, if your world is building paths, you have to know all of the resources and you have to have control of all the resources. Because what you're doing to make a call is finding unused path segments and chaining them together. And if somebody else owns those path segments and doesn't let you grab them and chain them together, or if they're assigning them to a different call, you're hosed. Right? And remember that we started this in the days of relays and people plugging jacks into patch boards. Right? There wasn't any electronics, there weren't any databases, there weren't any computers. You have to have something that starts working in this very primitive technology, and then you scale it through about a century. And by the time you get to the 60s, you've got electronics, you could start to decentralize things, but you've got all of this infrastructure and a big, powerful company set up, and it really wants to be a centralized monopoly, because it knows how to work efficiently in that way. And that was true all over the world. Even phone companies that started out fairly decentralized turned into big centralized monopolies. A big issue for the military in the 60s and 70s was, we're worried about somebody dropping a bomb in the US. Is our phone system going to go down? And the answer is yeah, almost certainly. Lots of things will go down. But this system in particular is really structurally unreliable, because you're concatenating together a whole bunch of things, and they all have to work all the time in order for the system to work. That means that the reliability, which is the product of the failure probability of all of those elements, that's going up exponentially. If you put n things in series, the probability of failure is p to the n. That's a problem. So back when I was doing control systems in the 70s, Bell Labs was the world's repository of information on reliability and how to build reliable systems. They couldn't actually do reliable systems. What they would do is reliable elements. Their switches were all gold-plated. They would work forever. They all had modular redundant components and voters inside them, so if one thing failed, the other two would take over and work. They had to do this because their system was just incredibly unreliable, and the only way that they could scale it up to a national size was to make individual elements that were incredibly reliable. It's kind of the opposite of the internet philosophy, or the RAID philosophy, the philosophy you use in your service, which take a bunch of cheap components, replicate them, allow some loose agreement between them, and if one fails, you don't give a damn, right? Because there's lots of others. So you've got a system that's structurally reliable. You don't worry much about component reliability. So they're on the other end of the scale. And then a thing that really killed us when we started to do data, which is phone calls are this two-phase thing, because the system is all about building paths, right? So there's the part where you dial and connect to the far side, and that's, you're building a path through the system. And while you're building that path, the things that, kind of building a bridge across a river and you're standing on it to build the next section, right? Everything behind you is all committed. but nobody can use it because you haven't made the bridge yet. So that's not an issue for phone calls, where you can build the path in about a second and the call lasts for at least a minute, right? So that's a 1% cost to build a path. But if you're sending data packets, a second's a long time. So typical transcontinental setup times is best case about 100 milliseconds. So 100 milliseconds at a gigabit per second is 12 megabytes. That means that if you used a phone network, you would have to fetch 12 megabyte web pages to use the system at 50% efficiency, right? No web page is 12 megabytes big, right? You can't do what we do with networks when you have these huge setup costs to amortize. Because as the speed goes up, the amount of bandwidth of potential data that you're throwing away waiting for your connection to get set up is enormous. It's getting on the order of gigabytes, right? And we don't want to talk in units that are that big. Typically, we want to get some information that tells us what to get next. So there was a bunch of work that was happening in the 60s and 70s saying, oh, here's the core problem, right? We're either going to get a data network like ISDN, 64 kilobits is all God ever intended you to have, and if you make it slow enough, then the holding time really doesn't matter. And a bit's 10 miles long at 64 kilobits, so it only takes a few to go across country. But if we ever wanted to make a faster network, we had to figure out how to do faster setups. And so pretty much the entire US research establishment was aimed at that problem. Networking research was how to amortize the setup costs, and maybe we should worry about the reliability and some of the other structural things. But it went as an unspoken, unquestionable assumption that telephony was the right model for data networking. It was communication. Nobody did anything else. But there are these two guys, Paul Barron, Don Davies. Barron at Rand Corporation in LA, but he now lives in the Bay Area. Don Davies in the UK. They said, what if telephony is not the only way to communicate? I mean, there were other things. There were signal flags. There were Morse code. There were, through history, we've seen people doing lots of different styles of communication. Maybe we can adapt something other than the telephony conversational paradigm. And so they were free to change their point of view because Bell had put in a whole bunch of wires. And so they didn't have to worry about the problem of, well, how am I going to get a communication path between two computers? Just take it as given. There is a communication path. There's lots. The phone system's in place. Just use it. It's there. Let's split data up into little pieces because there's not an infinite number of wires between any two places. Not everything is connected with its own individual pairs of wires. So we're going to have to share the path. The only way that we could share the path among many things is to have the amount of work that we do per thing be controlled. Right? If somebody can send a gigabyte into the path and I can't do anything until that gigabyte has gone away, it's like mixing cars and trains on the city roadway system. You're going to spend a lot of time in your car waiting at an intersection for a train to go by. You don't want to do that. You want to have limited length things. It'd be nice here to not have big trucks. It would, just little cars. So Davey said, hey, yeah, chop it up into little pieces. We'll call them packets. And then Paul had this cool idea. His background was a mathematician. He said, let's use transitivity to get things together. So if you get one of these chunks of data and it's got in its header where it's going, and if it's not you, then figure out how to send it on. And I don't know how to figure out how to send it on, but I know I could statically configure that to get us started, and then we could figure out how to do it more dynamically. So this is a wonderful property, right? This, graph theory, if you do a closure on a graph, almost any graph is completely connected. As soon as it gets more than one edge per node on the average theory of random graphs says, hey, you've got the whole thing connected. And so if you've got transitivity built into the system, you don't need to engineer it. You just need to hook it up, and it's going to work. They wrote about this. Paul in particular published this in '64 in IEEE Transactions on Communications. Utter heresy, right? Everybody who did communications, the entire staff of Bell Labs, came out and said, this can't possibly work. He's ignored everything that makes a phone system work, that makes it scale, that makes it reliable. Fortunately, there was this guy, James Licklider, director of ARPA at the time, who knew nothing about networking, but he kind of liked the paper. And so he tasked BBN to build the network that Paul Barron had written about. And they turned it on in September '71, and it worked like a champ. Now, it was built on top of the existing phone system. It never could have been built if it didn't have those wires available. It was using those wires. It was using them in a different way than the phone company was using them. I mean, it assumed that the phone company is going to build this little path. That's what it does really well. And we ignore that. And wherever the bits happen to get, that's where they get. And then the node will figure out where they need to get to next. And so it was a network that hooked itself together as a mesh and figured out you only had to worry about connecting adjacent hops. And it's going to figure out the rest. So you couldn't make the network without Bell's work. You needed to be able to put bits into it. They didn't really care how fast or how slow you put the bits in. Nice thing about the design was it's completely speed agnostic, unlike the phone system network. So they took whatever crummy modems they could get at the time, which were 56 kilobit acoustic couplers. It was passing packets pretty much from day one. The ideas were so simple they couldn't fail. But if you look at it, all the telco people said with very loud voices, that's not a network. That's just a crummy way to use our network. You're taking our wires, you're sending on the paths that we create, and you're putting a lot of extra gunk on it so that you use it really inefficiently. And you know, that's always going to be the case. When Copernicus first wrote his paper on planetary motions, the predictions that he gave were really crummy compared to the Ptolemaic predictions, right? The Earth-centered universe, astronomers had had 3 centuries to work out the math of that, and they'd gotten really, really good at it. And this new system comes along, you know, it's 1 week old, and hey, you know, it sort of tells you where stuff is, but, you know, don't set your compass by it. It's pretty crummy stuff. And so you've got this new packet network. It's a pure overlay. It is really inefficient compared to the telephony network. The telephony network didn't have anything like addresses in it. They were all implicit. And it took a long time. It took like 10 years to most people could look at that network and see the IP network really, it didn't matter whether it was over a phone network or over an Ethernet or over a token ring or over a satellite or over a radio. It was really completely agnostic about the delivery technology. And you really shouldn't care that it was an overlay. One of its features was it could be overlaid on damn near anything. And if you got hung up in, oh, but this is just an overlay and the real network is underneath it, you missed the whole point. The point was they changed the point of view. They were looking at the endpoints and not at the paths. And when you do that, you can make this agnostic network. But at the time, they didn't convince anybody. The entire research community was still driving the truck down this road of how can we do fast setup? How can we do fast connections? So almost the entire research community. So there were these 2 other guys, Stanford professors, real straight, you know, all the networking had been done on the East Coast. But these 2 guys, the ARPANET was this massive success. It just worked. Everybody wanted one. Everybody wanted to communicate with that kind of technology. And so dozen different military organizations, a dozen different academic groups, they were all building their own networks. They all had to, sort of piss on it and make it theirs. So all the protocols are different, all the encapsulations are different, all the addressing structure is different. But the idea is they're all packet switch networks. And Vint looked at it and said, oh, we could concatenate these networks. Now, if you've got a phone network where you're building paths, the topological details are all that matters. So you have to have detailed knowledge of the topology and detailed knowledge of how the links are assigned. When you're building a packet network, when you apply Paul's ideas, the topology doesn't matter. Nothing could be more irrelevant. The topology is something that a packet sees at the instant that it's going through a network. But externally, you don't see anything but addresses. You want to name the destination node and nothing else. Since all the topological details were irrelevant in these packet networks, Vint says we can leverage that. If we have a common encapsulation format and a common addressing structure, and it only has to be common where two networks touch. So it's the time when borders start to matter. In telcos, there are no borders because there's only MOBEL, there's only the telco. But he said, everybody can go and build their own networks, and we can transit them. We'll get the same transitivity that you get in a single network. So they wrote the specs for that in '74. And in '77, they demonstrated it by sending data from a SRI van over packet radio, over the ARPANET, over satellite, back through a whole bunch of gunk. But they were basically sending bits across the world and back again over a bunch of different networks using this concatenated networks idea. But Vint could never sell the Catanet name, just had too many letters in it. The military likes three-letter acronyms, so it became TCP/IP. And it won. It worked nicely. If you're doing this style of packet network, you nail all of the phone system problems. Now, because on a packet-by-packet basis, you can choose alternate paths on failure, rather than the system getting less reliable exponentially as it scales up, it gets more reliable exponentially as it scales up. Because as you make it bigger, there are more different ways to correct for a failure. So you flip the combinatorics around. You never set up anything, you just launch a packet. If the network can't deliver it, it throws away. Okay, I don't care, I'll launch another one. Because you're not doing any setup, you're completely bandwidth agnostic, because there's no setup to amortize. Right? So you just send your packet. You don't have to make this strict hierarchical routing system that the telcos had to make, where there's high bandwidth at the top. Calls could take a maximum of 5 hops, which means 3 hops from the leaf to the center of the network, maximum that you would ever take. They did that for stability and engineering concerns because it was the only network that they could control. And the core issue there is scheduling problems. All scheduling problems are NP hard. And like the rest of us, they couldn't solve an NP problem. If you restrict it to a subdomain, particular subdomain being hierarchical allocation in a hierarchical bandwidth tree, you can solve the problem because you can aggregate things as you go up the tree and make sure you've got enough bandwidth for it. IP network, arbitrary mesh, we don't need a hierarchy. We're not scheduling anything. You launch your packets. If the planets align, it'll go through. It almost always goes through. And if it doesn't, then the end nodes will fix it up. And we got one freebie. So those were the 3 known problems in the telco system that Barron was able to convince the glitter at ARPA it was really important to make this reliable, scalable system for military purposes. One thing they found when they deployed it was they've got this adaptive routing that if there's a failure, you route around it. But that works from day one. From the time you plug something in, it's now a new element of the system. It can be used by the system and it can use it. So an IP network hooks itself up. A phone network does not hook itself up. right? Phone networks are all about armies of people spending their lives in manholes, punching down copper wires onto 50 blocks. Right? And you don't ever do that with a packet network because the addresses are explicit in the data. They're not implicit in the particular pattern of wires that are on the switch matrix. So I don't know if your network is open, but if it was, I could plug my laptop into the Ethernet. It would be able to route packets out. Packets would be able to route back to it. And I never punched down anything on a block, right? I never had to tell the network about my connectivity. I just need an address. And that makes it really easy for anybody to deploy the network. This is horrible for telco because it's a democratization. It moves a lot of their value out into commodity marketplace. You can just buy these devices and need them, and you don't need big company technicians to hook them up. But it was great for getting ubiquitous communication infrastructure. Okay, so like I said, TCP/IP1, it was a terrific way of doing data networking. It is still a terrific way of doing networking. It nailed this problem so well that it's framed our thinking, just like the phone company framed our thinking. We now think of data communication as being IP data communication, right? It works. The problems that we're seeing today, the fact that our seamless connectivity isn't really seamless connectivity, that we have firewalls and VPNs, ad hoc synchronization protocols, they're not the failure of TCP. They're a success disaster. It's created this ubiquitous communication environment. Anything can talk to anything pretty easily, can hook itself up dynamically, can unhook itself. The network, the infrastructure all fixes itself up. Things like the web were put on top of it, which moved all of the world's information into digital form and made it accessible. And so now we've got this wealth of information. We have the wires to access it. We've got machines to access it. That was not the world that TCP/IP was connected in, or was created in. When it was created, machines were these huge things that lived in glass-walled machine rooms. They had 1,000 people would use the same machine, right? There was 2 machines at MIT, and there were 2 machines at Berkeley, and there's 1 machine at Arizona where I went to school. Those machines would get connected together with wires. There wasn't a lot of data. You were putting data in on card decks, and you were getting it out on printouts. You wanted to be able to remotely use resources, and you occasionally wanted to be able to pull a card deck that somebody had put on the disk from their machine to your machine. But you had not a lot of information, a lot of users per machine, not a lot of machines. And that was the model of connectivity as this networking was being rolled out. It's kind of a bad fit to today, and these are what I think of the problem. The thing that annoys me most is that connected is this completely binary attribute. The internet is a thing, one thing, and you're hooked to it or you're not. No middle ground. And if you're hooked to it, this wealth of information is available to you, and if you're not hooked to it, you're hosed. And so if my PDA or my phone or my laptop aren't hooked to it, then I'm hosed, and I figure out some protocol to synchronize myself or download my mail ahead of time. Getting connected to this global internet, because it's a single huge planet-wide artifact, it's a pretty heavy-duty operation. The only way you can do it is by getting this IP address that's globally known. You can get local NAT addresses, and there's some box at your border that turns that into a globally known address. But at the bottom, the protocol somewhere want a globally known address. And that address has to be relatively stable. It's not an address that you can use for a millisecond and throw away. It has to be, the world has to know where you are, and you have to know where the world is, which means that it has to be a topologically stable address. You have to know what the connectivity is around you. And the time scales, as we've scaled the network up, are pretty gross. The addresses have to be stable on the minutes to hours time scale, otherwise data just loops in black holes. So those 2 things result in these 3, that connecting to the net's a real heavyweight operation. That means that you want to carefully control those connections. Because of the topological stability requirement, the net hate things that move. You want to put a net on a train, well, good luck. There's a whole bunch of ad hoc infrastructure to do that. Put a net in your car, well, if the cell towers cooperate, maybe you can do it, but you're covering over the movement at layer 2. And the neatest technology we've got today is broadcast. We've got all of these radios that are hooking things together, and we really can't use the suckers from our networking stack because the net hates things that broadcast. The protocols weren't designed for it. The protocols were designed for a conversation between two applications on two machines. The conversations are point-to-point conversation. So we take all this data that's being broadcast out on our radios, 10,000 radios hear it, and 9,999 throw it away, and only one will look at the data because it's got his address. Now, maybe something like, hey, there's an accident 2 miles down on 101 that all 10,000 of those radios really cared about, but they have to ask individually. We got in packet design, the company Bob and I were at, we got a chance to look at the data on the routers downstream of NBC servers for the Olympics. At one time, their main router got severely congested. It's when Bodie hit the pole on the slalom. In that router, there were 6,000 copies of the same data. Right? Everybody was pulling down the URL. Poor router can't do anything about, you can't optimize it because it's dynamic content. It's all going out as separate conversations. All the router knows is I've got 6,000 separate TCP conversations. It's the same data. Right? If you could broadcast it, you could turn that, both the router and the downstream links from the server, reduce their bandwidth by 3 orders of magnitude. But our protocol architecture doesn't support that. It works at the conversation level. Okay, so I said this. The main issue is the success of the protocols change the world. And when you get a new world, the protocols may not fit the new situation. It doesn't mean they're wrong. It doesn't mean that you aim the entire US research community at, oh, let's do a replacement for TCP/IP. It's not the solution that's broken. It's the problem that that solution addresses has changed. There's a new problem. The change is this. When the protocols were rolled out, they got rid of the telco path building model, but the thing that the telcos enabled was conversations. When Bell first rolled out the phone system, he didn't know what the hell people were going to use it for, right? He just wanted to get phones out there, but there were no phones. You didn't have conversations with people on the other side of the planet because there was no technology for it. So he wanted to put these phones out and figure out how people were going to use them, and what evolved was phone calls. So in the 60s, people looked at it and said, oh, what we want to do is a different way of doing calls. Right? We want this side effect in the phone system to actually be the centerpiece of our system. So when you design the TCP/IP protocols, you make conversations be the central architectural element, right? As opposed to the phone system where they're what happens by accident after you build a path. So that was great. It got us going. But that's not how we use the network today. People don't want to have conversations. What they want is their web page. Right? Any of the measurements that I've seen recently saying that the high 90% level of traffic is people trying to get some name chunk of data. They hand in a URL and they want to get something back. That's not a conversation. It's not a conversational model. It's sort of the computer equivalent of, does anybody have the time? Does anybody know where we are? Right? That's that kind of interactions and dissemination. It's a point to multipoint or multipoint to multipoint. It's a very efficient information transfer. It's been used for much longer than conversations. Conversations are a special case where the multipoints collapse to one. So it's a pure superset of the conversational model, but it's a different model. So when you're doing a dissemination, What you're interested in is the data, not who gives it to you. Now, you can do disseminations over a conversational network. That's what we're doing. It's what we've been doing for a decade. It doesn't work very well in at least three important directions. The one that's biting us most today is you can't make a viable security model out of that. Because if your network works in terms of conversations, in terms of virtual bit pipes, what you can secure in the network is that bit pipe, right? So we know how to armor an SSL connection. And I can armor the SSL connection to my mail server, but it doesn't stop the spam, right? It's, oh good, these bits came from my mail server. They're garbage, but they came from my mail server. The network has no knowledge of the content of what it means, right? So it can't do a security model at the network level because it's blind to the data. Like that NBC server, you get a tremendously inefficient network because the network can't distinguish the same content bound for different destinations. And so it can internally arrange to optimize the delivery of that content, doing something multi-point delivery. It can't leverage things like broadcast. It can't split data inside the topology, do flooding style protocols, because it doesn't know about the data. It knows about the conversations, the TCP/IP headers that wrap the data. And up at the user level, we've got all of these apps that are dealing in dissemination style data, that want to deal in URLs, mail messages, sensor readings, individual voice packets. And our network model is, okay, to write this app, I have to figure out what server to open a TCP conversation to. And that has nothing whatsoever to do with the app, right? It has nothing whatsoever to do with the problem that you're trying to solve. And so both the app writers and the users have to do this horrible plumbing operation in their head and in the network. If you've ever set up a VPN to get at the internal websites or get your email when you're offsite, right? You're doing this nasty, ugly plumbing to solve a problem that the network should be able to solve for you, but it doesn't know your intent. And it can't phrase what you want in terms of conversations. Okay. So if we wanted to do a more dissemination-based networking, the idea is you change your point of view to focus on the data, not where the data lives, because it doesn't have to live anywhere. Right? Data is named. When you want some chunk of data, you present its name to the network. And it doesn't matter what kind of networking technology you've got. Use them all. It's asking, does anybody know where we are? Pass this data out to the network, hope somebody can give you a reply. Anything that's got the data, view it as broadcast and unicast. If something's got the data, it can give it to you. If it's some kind agent like the equivalent of a router that kindly forwards your packets, instead it could go get the data for you and then give it to you. The big issue in this is it's totally bogus, but right now, today, we decide that data is authentic if it comes from the server that originated the data. So I'm going to believe my copy of the New York Times front page if and only if I get it from the New York Times server. Now, those bits got hauled halfway across the planet. They went through a lot of routers. They could easily have been corrupted. They cache reconstituted. I could be getting Fox News for all I know. But our only model is you've got to secure the pipes. I think I would know if it was Fox News. But if you're going to data dissemination, where you get it from doesn't matter, it can't matter. You got to be able to trust the data based on the data. And that means doing some crypto things to the data so that you've got some basis for trusting it. And that actually works in general, right? That works in the face of proxies, staging data, doing lots of things. If you can get the data, you look at it and say, yep, that's good stuff, or no, that's bogus. So at the architectural level, if you're doing dissemination, you've got to have a security model. You've got to be able to assign things and make some sense out of them. Let me see if I can make that more concrete. So the model is, I do a request for today's New York Times. And I usually don't know what today is, so I want to make this generic request. Give me today's New York Times, and I'm just sending that off into the ether, hoping that something's going to come back. So if I get back a response, it wants to have the name I requested, because that's used to vector the data to me. The data is moving via diffusion. There's a request that sort of sets up the channel, and then data flows down that channel. So something is remembering that my port, at least someone had asked for New York Times, asked by the generic name. The data's actually got a specific name. Today's New York Times has got the date on it, and it's a particular web page. It's the front page. It's the starting point for getting the rest of the data. And then down here is just the text of the front page. And there are two things that I've got to secure when I'm getting this data back. One is the binding of my generic name, today's New York Times, to the specific name of this edition of New York Times, the August 30th, 2006 edition. And so I need some sort of method, authentication check, and probably the associated certs that ties together those two names. The NewYorkTimes.com has signed the fact that 2006-08-30 index.html is an instance of NewYorkTimes.com today. And when I set up my contract with the New York Times, I got their cert, so I can look at that signature and say, yep, this really is from New York Times. It's not from Rupert Murdoch. And the other is the binding of this specific name to the data. So even if those two names are bound together, and I can say, oh, this packet came from the New York Times, but I need to know that Rupert didn't rip off the content and replace it with his own. So I need that name binding to the data. The data itself, I mean, its real name is probably like a SHA-1 checksum, right? It's some cryptographic string of bits that represent the data. So it self-authenticates or self-identifies, but I need to take that identity, that SHA-1 of the data, and put it together with this name and bind them together with a cert. So that's what I mean by authenticating the data, and both the bindings and the data itself. It's all we ever do to get data is ask Google and then click on links, right? So you're following this path through meta information in order to get to the real information. You got to verify the path if you're going to have any trust in the information. But when you're doing that, you don't have to change very much. So this was the New York Times webpage. And this is some goop that I added on so that I could authenticate these bindings. But this, the page self-identifies. I can SHA-1 any web page. This stuff doesn't have to be packaged with it. I can just stick this somewhere else. And separately, get the credentials and get the data. So I could make an appliance that I sit at the edge of the network that handled dissemination for me and would at least give me the benefits of broadcast and distribution over enterprise campus-sized things without changing any infrastructure. Right? Basically, it's collecting data, collecting credentials where it can, mushing them together and sending this out on the wire in response to requests. So it's a nice incremental deployment, a nice overlay way of laying out networks, because what we're doing today is dissemination. We just can't trust it. So top-level design philosophy is data's got a name, not a location. When I say this is really hard talk to give, when I've tried to give it before, the first thing I get asked is, but this is just caching. And it's not, right? It's a different, the effect is very much the same, but your point of view is completely different. In caching, you say, oh, the data lives there, but I've got a copy of it here. And my model is the data doesn't live anywhere. Wherever it is, it's great, right? Wherever I get it, I can authenticate it. I know whether or not I can trust it. I can ask the world, anybody got this data? And I don't care where it is. And that's not caching, because I'm not moving it from its one true location to some other location, right? it doesn't have one true location. You can only do that if you do the second. Integrity and trust are properties of the data, not of the way that you obtain it. And you have to be able to develop integrity and trust from the data itself. This is by contrast to, say, the Microsoft Authenticode model, where you download this update from Microsoft, and there's a little window that comes up and says, do you trust Microsoft? And the answer is no. I kept clicking no, and my machine never got updated. I don't, right? But their model is, do you trust their delivery mechanism? They're basically asserting installing this update won't cause financial harm to Microsoft. Great, but that's not what I want. I want my machine to work. I want to know what you're going to do to my machine. I want to know something about the data and the operations you're going to take, but they can't tell me that. Right? So I want properties of the data where I don't have to trust remote agents, that the data itself lets me figure out what it means and who sent it, how it's connected to the world. And there's always been this tension in the CS community between different ways of moving bits. So the telco people move bits over these hardwire connections. They don't need any buffers because they have a master clock in Kansas that schedules everything on their network, right? So things never interfere. They all have their little dedicated time slots and they move around. And so their religion was the only true bits are bits in a wire. And when these data networking people came along and they put in buffers because they didn't want to schedule, so data may land at the same place in the same time. And that's great. You turn some of those bits in a wire to bits in a memory, put the others on the wire, and then you take the ones out of the memory, put it in the phone people look and go, buffers, that's not networking. Networking is cut through. Networking is moving the bits to the wire. And those bits that sit in a memory, those aren't real bits. And then the networking people would say, oh, those people do databases, they got data on disk. We do networking, we do distributed computation. So there's like way too much religious fundamentalism already in this country. There is no one, bits are bits, they're all good. And anything that moves bits, I don't care if it's a disk, a wire, memory, USB stick, running around on your bicycle, great. Yeah. If you move bits, time or space, you're part of a network. You're doing a good thing. Okay, so you get some wins if you do things this way. One is the communication win, and you can do way more inside the network on behalf of users because you're communicating to the network what you want rather than some meaningless abstraction. You're putting, I say, I want this data. And there can be something in the name that tells you even more about the data. I want the contents of my mailbox in a way that's secure, implicit in the fact it's the contents of my mailbox. If I'm not on a firewalled network, make a VPN to get it for me. If I can say the intent at the top level, I can do things lower down to concept the right semantics. Most of the problems that we have in congestion today, we've got this high bandwidth core because a fiber holds terabits, right? Much more data than we have available to send. We've got these skinny tails that connect us out to us. And all the congestion that you tend to see when you're networking is congestion from the core to you along this tail, right? But the end of the tail where the data lives is in your service provider's world. And you're sitting in your home PC world, right? And you can exactly control the data you send to him, so you never have a congestion issue. You can always send what's most important first. But you have no way to say what he should send to you, right? And because of that, I wait for hours while my son's gaming traffic is piled up on the network headed down our link, right? And my email is way more important than his gaming traffic, at least to me. So I would like to be able, and I pay the service provider, so I would like to be able to say to the service provider, send my stuff first. But there's no protocol for that. And the people that want to do QoS are the service providers, and they want to make it end-to-end because they can extort more money out of Google if they say, oh no, pay us for end-to-end quality of service, otherwise I deep six all your bits, or half of them at least. And they're not interested in making the tails any better because that's just a really small, I don't have much money. Google's got way more, right? So go after the big targets. So you get an architectural focus and sort of the wrong kind of QoS, things that will make things better. If you're doing dissemination, you get data in response to a question you ask. So it's really request response. That doesn't mean stop and wait. You can ask a lot of questions in parallel, right? But the order of your questions is the order of importance. So if I can arrange on my local network that I always ask for my email before my son's gaming traffic, and I run the gateway, then I will get good service from the email, right? And it's entirely in my control because I can control the requests. What happens when you do dissemination, because there's this symmetry, it's not a pipe from the service provider to you down which bits are blasted and you have absolutely no control over it. Instead, you get a fine-grained control at the data item level because you're asking for things individually. And we don't have the Olympic server problem. The network is dealing entirely in content. It's not having 6,000 separate conversations about Bodhi's pole incident, right? That's just one incident, one named piece of content. So you can distribute it as efficiently as you need to, no matter how dynamic it is. Yeah, so this I already said. You get rid of a lot of religion. Bits are bits. The bits in a wire and the bits in a memory and the bits on a disk. As long as you can name them uniformly, you access them uniformly. And so you don't have to do the moral equivalent of GNOME VFS, where you put in this huge application layer to try and accomplish the same thing. You put it in at the network architecture layer. Since you're not talking to nodes anymore, the reason that you're there is not so you can have an intimate one-on-one with google.com, right? Instead, you're just presenting this URL and saying, help, somebody find it. There's much less need for global topologies, global naming, particularly when you're doing something that's really local, like a sensor network. If I wanted to know what the temperature in this room was, or if I wanted to know directions to the nearest espresso machine, the room could be broadcasting it to me and it wouldn't need to IP wrap it, right? It could just be information that was wrapped in MAC layer encapsulations, and I can use proximity and diffusion and very simple local protocols in order to move that information around. Because you don't care about the topology, you just care about the data. And similarly, since we don't care about data living for a time in buffers or on disk, we can still access it by name. We don't have a conversation where there's always a real-time aspect. The fact that you've got intermittent connections doesn't matter. You can still get at all the data. If anybody remembers it, they can give it to you. So security terms, since you're making trust be architectural, it's really easy at the network level to make farming and phishing and spam and all of these imposter attacks or unintended sender attacks. They're just impossible. I mean, because you can tell from the data that you've got who sent it, what it is. You can never do that in a connection network, right? By its design, a conversational network wants to be completely agnostic to its data. It wants to be transparent. It's built that way from the ground up. You want to be able to ship anything over a TCP connection. That, when the protocol was designed, it was important to make it completely agnostic. But if it's completely agnostic, then you can't do a trust model. Anything can be in that pipe, and you don't control the other end. You're putting the trust in the data and user level objects and the stuff that you ask for. So you don't care whether you got it over SSL. That's not going to help. And if some, this is purely hypothetical, but if some big greedy phone company wanted to extort money from you, they have a lot of trouble doing that if you can communicate over anything that moves, literally anything that moves. You say, hey, you're not going to move our bits? No problem. There's a plane flying overhead. It's got a disk in it. My bits go up, they go to the other side, they come down. I don't care. right? Anything that moves bits, I'm flooding the data, so if they don't get there on your wires, they'll get there on somebody else's wires. It's, like the original IP network where you could bomb the hell out of it and it kept working. On this network, you can QoS the hell out of the center and it keeps working, right? Because the network doesn't matter much anymore. The way that you're moving bits around is this global diffusion process. Hello. So there's a little bit of stuff to figure out in order to do this. There's some stuff that's probably pretty easy because it's all been done. One is being able to check the integrity of data just based on the data. Well, that's something that we had to figure out for privacy-enhanced mail. It's, there's already a worked example, probably not the greatest example, and it's a much more limited context, but at least a problem of this nature has been solved in a fairly convincing way. And the trust structure that has been, that you need to embed it in, that's also been worked out. So there was this complete disaster foisted on us called certificate hierarchies that have never worked, and they have no trust at all associated with them. 2 years ago, VeriSign sold a root certificate to Microsoft to some unknown party, still floating around. You basically can't trust the people in which you impose, in a certificate hierarchy, the root, you've got to have ultimate trust. But these are people that make their money selling stuff. They have a lot of minimum wage workers, right? It's really hard to put ultimate trust in that economic structure. You can get, via things like Zimmerman's Web of Trust, get much more distributed community action. And so if you use PGP models, you can get some pretty good trust in things. You don't want the web to be any harder than it is today. So we've got a model for creating content that is, you stick data in a directory somewhere, and now you've created content. Keep it that model, but I want to be able to trust that data. I want to get some of these signatures. But that's okay. Make the repository do it. Right? If you've got the permissions to shove the data in the repository, that should be enough permissions to attach a cert to the data that says, okay, I will attest to the fact that this is the data that was put into this repository at this time. I'm not going to tell you that it's good data, but I can tell you that, yes, this is the legitimate copy that was first created under this URL. So there are models for how to do that. PARC's working on a system that they call usable security, kind of an umbrella project. They've got a model for how to do repositories in that automatic way that they call instant PKI. And UT Austin has been doing some wonderful things in distributed networking, peer-to-peer networks, very distributed services. They have an instant BitTorrent model that they call Snakebite. It's actually being funded under Google Summer of Code, that has a similar sort of repository, but also registry models that are in it. So I think you could sort of do a high-speed collision between these two and get secure, absolutely painless entry. And then lastly, you got to be able to find stuff. Well, Google's nailed this problem, right? Nobody remembers URLs. Nobody keeps bookmarks anymore. What you do is remember some search terms and you type them into Google, and then you search the page to find out what you want. So start with that model, right? Maybe you've got a URL. Maybe you search. If you've got some information that you want to spread around or some queries you want to spread around, we've got a lot of ways of doing that in this kind of model. Epidemic algorithms, which we've used for years on directories, directed diffusions, where you set up channels to constrain the amount of data that leaks outside the path where it's wanted. You can use small world graphs so that you can do very efficient data location for subsets of data, anything where you can define a center. So there's a lot of themes that some smart people might be able to figure out, not me. Since you're getting everything by names, you want to spend a lot of time on exactly what is a name and how you want to do naming. Biggest thing is you want all your content to be immutable. Once it's created, it goes out in the world and you've lost control over it. Right? It's now out in the world. That means that if you want to update something, what you do is supersede it with a newer version. And that newer version should reference back to the old version and say, hi, I'm a newer version of the New York Times. The one that you've got is probably obsolete. That means that wherever the data is, you can use it. You may have to do some work to find out that you've got the most recent copy or the most recent copy that's accessible to you, but you can use all the copies that are out there. So to do that, you want to be able to put sequence and time information, version number information into names. That's easy, but something that you need to do and tie into the verification, authentication machinery. You don't ever want to send huge things across the network. You want to take huge things and split them up into small pieces. It's good for the network, for the users of the network, because if you've got a lot of small pieces and you've got a lot of paths, you can send the different pieces over different paths and get much higher effective bandwidth, potentially much higher reliability. It's good for the user because the user gets way more control. Because you're asking for things a piece at a time. You don't have to wait for the entire download of this week's GCC to come down before you can get the next packet in your VoIP call, right? Everything's little pieces that are handled more or less independently, and then we've got lots of memory everywhere, so we put the pieces back together into a big thing at the end. And as long as you can do the segmentation, and we dealt with it in the naming, then the real-time media, I mean, I was co-author on the RTP, on the VoIP protocol. That was designed as a dissemination protocol because we were worried about going through voice gateways, about recording conferences on disks and replaying them. So every little voice packet, every little video packet's got a timestamp and a sequence number on it so that anybody can reconstruct the entire conversation. And it doesn't matter where you get it from. And it doesn't matter what the temporal characteristics of the medium are because the time information is all explicit in the data. And I'm sure I've got a slide that says that over again. That's kind of a general statement. If you look at the big advance that packet switching made over circuit switching, there's a lot of information that's completely implicit in a circuit system. The time slots that each piece of data goes through, they're never known by the data. The destination of the data is never known by the data. All that you send across the wires is the actual data itself, but no addressing, no meta information. If you're doing that, then you can't possibly repair from failures because the data isn't idempotent. It doesn't tell you anything about itself. It doesn't tell you where it's going. It doesn't tell you what path it's going to follow. So you can't fix the path for it because you don't know the path for it. The big advance in packet switching, right? One of Paul's first insights was put addresses on the packets. Yeah, you use a few bits, but you get this massive increase in reliability because now every packet tells you where it's going and where it came from, right? And so now, wherever you are in the network, you know what to do with the sucker. You know if it's for you or if it's not for you. If you know where it's going so you can figure out a way to get it there. So making implicit information explicit suddenly enables a whole bunch of new functions, new use cases. It's easy to screw this up. So when ATM, the telcos networking, they put identifiers in their little 54-byte cells, but they used this local identifier. It only had meaning to the two switches on each end of a wire, right? And it was rewritten on every hop. So you got this thing which got rid of the time slot assignment on a trunk, but it had no value at all in terms of the system characteristics. It didn't make anything more reliable. It didn't let the destination switch fix anything up because it still had this number which had no meaning except for the wire the data came in on. It had no larger context. So you give a few milliseconds thought to this problem because you don't want to screw it up. But you do the analogous thing in dissemination where you take information that's implicit, like time information or version information. You say, oh, if I'm connected to sourceforge.net, then the version of GNOME that I'm pulling over is the most recent GNOME because this is the master repository. Instead, you put the version information explicitly. You have something that tells you what the most recent version is, and you request that version. Hello, wake up. There's some harder stuff to do. Like if you want to do a world scale network on this, you've got to work out the incentive structure. which is the equivalent of TCP's congestion control. You've got to make sure that people get everything they need, but they don't shut out other people, so they get some kind of fair share. Since anything can both source and sync data, you want to really drive the BitTorrent ideas of you should redistribute content, and it's in your interest to redistribute content because you'll get it faster if you agree to get people to other, if you're going to use people riding their bicycle across Africa as a communication mechanism to network the third world, you really want a lot of incentive on data sharing. And you can build that into the flow control. BitTorrent's done a bit of it. In all the peer-to-peer systems, you have a tremendous problem with miscreants and freeloaders, people either dumping in bogus content, taking but not giving back. You want to architect that out at the network level. I mean, you want to make that as hard as possible. Exactly how you do content routing, what the policies are for redistribution. You get some stuff that you really didn't ask for, but you're going to carry it along in case somebody else wants it. I mean, that's fine. My phone's got 4 gig, of which 3 gig are empty. I'm happy to carry some extra data, spread it out in the world. But exactly what do I carry, right? What's likely to be useful where I'm going, or do I just grab everything that's in my environment? And then there's liability issues. What if one of the things I'm carrying is a virus, and it comes back to me and say, oh, I'm going to sue your pants off because you gave me this virus. I go, hey, it was encrypted. I didn't even know. So when you're architecting, you want to architect around those issues or look at the legal ramifications. And then you've got this content that either deliberately or accidentally is going to get corrupted. And you don't want to be checking every piece of content everywhere as it's flowing through the world. So you would like a system where you can mostly distribute content, but if somebody says, hey, that copy of GCC that you gave me was completely bogus, you want to be able to go back up the distribution path and nuke that copy so that you don't hand it on to poor unsuspecting people. And there are gossip and reputation and epidemic systems that do that kind of lazy invalidation. So I think we can work that out. When we were working out problems like this on the original internet, we had sort of, I tried to phrase this in a way that would be acceptable to Republicans as well, but there's no intelligent design in the network, right? It was just sort of hooked up. So we actually had this evolutionary force, which was the evil empire, and they were going to bomb the daylights out of us, and we wanted to make a network that would survive that. And that really clarifies your thinking. It gives you a way to test all your design decisions and say, okay, well, if they drop the bomb, is this going to work? Do we have state spread out through the universe, or is it concentrated, nicely distributed? Do we have routing information? What's happening? So you look around and say, okay, if I were doing a new network today, the evil empire is gone. It moved to Washington, but what do we have that's an equivalent? And I see, there's lots. I mean, we've got epidemic of greed. There've been 5 generations of peer-to-peer systems. They've all gotten better. They've all gone from very centralized ideas, centralized names, centralized content, to very distributed names, distributed content. It's all been basically driven by these guys and their endless lawsuits. So, I mean, it's great. There's a lot of drivers that I think will help us make the right kind of content network. So I'm finally done. TCP/IP is this huge advance. We no longer had to plumb up our connections, but now, 30 years on, we've evolved to the point where now we have to do plumbing at the data level. In order to get the data we want in the places we need it, we have to do a bunch of low-level connection plumbing. If you move your view of networking to the data level, change your point of view, a dissemination architecture says, no, let the network do the plumbing, like it should. This is being done, right? I'm not talking about anything revolutionary. The work's going on. It just seems to me to be sort of fragmented and ad hoc, but there's Akamai, there's BitTorrent, Sonos is selling music players that you just sort of set up and they spread your music around. Apple's got this nice rendezvous system for getting at resources and various kinds of information. So I think there's a demonstration need that, there's lots of motion. And lastly, we're killing so many brains in academia. It's like we wasted 20 years of grad students having them work on circuit switching, and now we wasted 20 years of grad students having them working on replacing TCP/IP. Don't replace it, use it, do something new. And so I'd like to kind of push the world to a different point of view. And I'm done. Questions?
What do you think of BitTorrent solution? What problems do they have?
So I'm supposed to repeat the questions. What do I think of BitTorrent as a solution, and what problems does it have? It's sort of a long discussion, but the biggest issue is the temporal binding when you're doing the torrent distribution. So client talks to a tracker, basically gets a list of other clients that are busy downloading this content, and can talk to those other clients and get pieces that they've already got in addition to getting some pieces from the tracker. Because there isn't any fixed distributed memory in the system, the only people that are eligible to give you the content are ones that are getting it themselves. And that means it only works for big content. So what you see going over torrent is movies and the latest KDE distribution, big honkin' things, because the individual downloads have to last long enough so that you have a big population of other downloaders on which to draw. Because the protocols that you use to get them are entirely topology unaware, the initial, your initial seed might be anywhere, the initial downloaders might be anywhere. You do some statistics as you're downloading and preferentially use ones that are close to you topologically, but there's nothing in the protocol that can set that up. It can't do any learning, it can't use any location information because basically it doesn't have a way of distributing the trackers. And if it did try to distributing trackers, you'd be in the Nutella world where you never know when to forget everything. Everyone who ever asked for this content is registered as a possible source of the content. And so you've got 10 billion places to get it from, most of which are unreachable. And so when you do a content distribution network, you still have to think about locality. I mean, eventually you want to be able to get stuff from anywhere on the planet, but get it close first. And that requires really architecting how the requests happen. But you can't do it with something like BitTorrent. You don't have control of that level of the infrastructure.
You talk about broadcast. What do you think about IP broadcast? Is it going to work? It's just extremely hard to set it up on a global scale. It may work on an enterprise scale, but it's going to be the solution.
So I think the question was, I talked about broadcast. What do I think of IP multicast? I mean, I love IP multicast. It made many things easy when we were doing the voice and video tools, and it's sort of an experience that underlays a lot of the thoughts about dissemination. If you've got multicast universally available, then you don't think about conversations anymore. You think more about disseminations, with conversations being a limiting, just a two-party case. But as you say, you can't scale it up. You can't make it global. My feeling is you shouldn't have to, that if you're thinking at that level, you're thinking too far down. That you want to think about the data and where you are right now, what's the good way to ask your questions and get your answers. And so if you've got room level link layer broadcast, that's great. If you've got enterprise level IP multicast, that's great. And you don't need it in the world, right? Because what you're trying to do is to get some copies of the data that are close to you or get the data closer to you, right? And so it's kind of, think like web proxy auto discovery, right? I can multicast a URL inside of Google, and that's going to hit the closest proxy, right, which will either give me the data or it will go fetch it. And if it goes fetches it, then it's got it, and so if somebody else is asked, they'll get the data from the proxy. And finding that proxy via multicast, resolving DNS names via multicast, it's very efficient because you can use the media efficiently. The topological awareness is buried in the network, so you don't get multiple copies of the data going over one link. And because the behavior is sort of like cache replacement semantics, the only thing that's unicast are the misses, right? So as you're pulling the data down, yeah, so one request went unicast, but the next 99 went multicast. And I think if you architect the system so it's got that kind of behavior, so as data diffuses from producers to consumers, then you get more of the cache locality semantics, and that means that you only need local multicast. And we should do a local multicast.
Let's thank the speaker, and then we'll have some questions afterward, but we have to shut down the video conferences and the videotape. So.